Welcome to the Electrical and Electronic Engineering lecture series. Your anchor person is Professor Michael C. Ndinechi. The topic today is AM and FM Demodulation / Detection. The process of extracting or recovering the information from a modulated signal is known as demodulation or detection. Demodulation of AM and FM signals require different methods because of their different characteristics. However, in general, linear demodulation is essential in both AM and FM systems in order to minimize signal distortion. Let's start with AM detection. Two main types of linear detectors are the non-coherent or envelope detector and the coherent or synchronous detector. The envelope detector is the most commonly used because of its simplicity in AM systems. Synchronous detectors may also be used for AM signals, but more usually they are employed for double sideband suppressed carrier or single sideband signals. The synchronous detector is far more critical in its operation than the envelope detector, since it depends upon exact carrier synchronization for its correct operation. Synchronous product demodulation. This involves the multiplication of the incoming signal with a locally generated sinusoid from a unit called the local oscillator and low-pass filtering the result in order to obtain the message signal. This is as shown in Fig. 1. For synchronous detection to be effective, synchronization of the locally injected carrier must be exact. To ensure exact synchronization, a pilot carrier of about 26 dB below the normal value is transmitted along. At the receiver, the pilot carrier is used to phase lock the local oscillator, or alternatively, it may be amplified and used as the local carrier signal. You can see the Fig. 1 here, VCT with the local oscillator multiplied, then low passed to feed to the other sections of the receiver. Envelope detection. This is the most common method of demodulating the standard AM wave and is achieved with circuit connection of Fig. 2A, known as simple diode detector. The envelope of the standard AM is independent of the carrier and phase. All that the envelope does is to extract this envelope without any need for synchronization. The circuit behaves like a half-wave rectifier. When the carrier is positive, the diode conducts and charges the capacitor C1, and as the carrier level decreases, the diode stops conducting because the voltage of C2 exceeds the carrier voltage. However, during the negative cycle, the capacitor discharges through R1. The VC of T starts increasing until the next half cycle, which causes the envelope to rise again. The sketch in Fig. 2B illustrates the output voltage. The capacitor C1 is charged and discharged with a time constant R1 C1, which is so chosen as to effect the complete recovery of the signal. It is required that the time constant be long enough compared with 1/F0. The simple diode detector has the disadvantage that output voltage, in addition to being proportional to the modulating voltage, also has a DC component. This DC component represents the average envelope amplitude, that is, the carrier strength, and a small RF ripple. However, this unwanted DC component of the wave is removed by the combination of C1 and C2 and the audio signal appears across R2. Figure 2A is the envelope detector circuit, and 2B is the input and output voltages. FM detection, usually called FM discriminators. Different types of discriminators have been devised, most of which operate on the principle of converting frequency fluctuations to amplitude fluctuations by means of some frequency-sensitive network, and following this conversion by an envelope detection. The amplitude changer produces an output voltage which is linearly dependent on input frequency. Ideally, the circuit should be insensitive to the amplitude changes in the incoming signal. This simplest form of discriminator is as shown in Fig 3 and is referred to as the slope detector. The block circled in blue is the use of an inductance as an FM to AM converter, then followed by the envelope detector described area. This very simple form of discriminator is not widely used because, although it is highly linear, its frequency to voltage conversion factor is very small. However, the discriminator conversion factor may be substantially improved by employing an off-resonance tuned circuit as the frequency-sensitive element to replace the inductance in the first block of Fig 3. Also, use may be made of the balanced slope detector of Fig 4 or discriminator, which is much more efficient and linear, although it imposes more serious circuit problems. Circuit diagram of a balanced slope detector. So, some other common types of discriminators for FM receivers or demodulation are Foster-Seeley phase shift discriminator, the ratio detector, and the phase locked loop detectors. The phase locked loop detector is the more widely used, so we'll talk about it. All the FM discriminators mentioned earlier suffer from the disadvantage of making use of inductors or transformers. These components are bulky and costly and are more complicated and difficult to align in such a way as to produce a linear frequency to voltage conversion characteristics. None are stable for IC fabrication either. An economical and convenient solution to this problem is found in a subsystem known as the phase locked loop. An FM detector using the PLL is as shown in Fig 5. Here, the incoming modulated carrier V of t equals AC cos 2 pi FCT plus phi is multiplied by the voltage control oscillator VCO output. V1 of t equals A1 sine 2 pi FCT plus phi 1t to yield some and different frequency terms. The difference frequency term is proportional to sine phi t minus phi 1t, and for small phase differences, this quantity may be expressed as phi t minus phi 1 of t. The difference, which is the error signal, is applied to VCO in such a sense as to drive its frequency towards lock. When in lock, phi t is approximately equal to phi 1t, so that the input to the VCO, which is a frequency modulator, will be proportional to phi t and hence to Vm of t. It then follows that the loop output is a close approximation to the modulated signal when the lock has been attained. Figure 5 that shows the FM receiver incorporating a phase lock loop demodulator. Note, not only is the PLL preferable to other FM discriminators for reasons of economy, its noise performance is substantially better than that of the discriminators at low values of carrier to noise ratio. Comparison between the synchronous and the envelope detection. For the synchronous detection, it requires carrier wave, involves synchronization of signal, also requires an external input from a local oscillator, and the detection is complex. For the envelope, carrier is not required, only the envelope of the AM signal is used. Do not require synchronization, no external input is required. Envelope detection is simple and very common. It is the most widely used AM detector. Thank you for listening. Please like, share, and subscribe. Drop your comments, requests, or topic you want me to lecture on in the comments section.